In this second lecture, we'll continue our first lecture and talk about how we will use continued fractions to solve the problem that we have presented. If you haven't watched the first lecture, you can click the information card to watch it. I'll also advise you to read through the description box before you start this lecture. Now let's begin. Let's start with today's question. It asks to solve for the minimum of b in the following equation, where 47 over 151 is less than a over b less than 34 over 109. A, b are positive integers. This is actually the question that we left on our last lecture, and we talked about Farey's fractions and how we will find the minimum when AD minus BC equals to 1 in the last lecture. In this lecture, we'll mainly talk about this question, where AD minus BC does not equal to 1. So before solving this question, we'll look at something that you can clearly see is important in this video, which is continued fractions. The definition for continued fractions is like this. We can denote continued fractions in this form, where a0 plus 1 all over a1 plus 1 all over a2 plus 1 all over ... plus 1 over an. We can also denote continued fractions in this form, left bracket a0 semicolon a1 a2 till an and a right bracket. In this lecture, we'll mainly talk about continued fractions where a0 equals to 0. Also, I would like to remind you that there's an important restriction on continued fractions, where a0 can only be a 0 or a positive integer, while a1 till an can only be positive integers. It cannot be 0. So after this example, let's explore the numbers in our question. 47 over 151. We can denote it like this, and 34 over 109 can also be like this. Notice that they all have the numbers 0, 3, 4, 1 as A0, A1, A2, and A3. The part that is different is here and here. 1 all over 2 plus 1 over 3 is also 3 over 7. So it seems like the problem asks for a fraction between these two. This means that a over b also needs to have 0 plus 1 all over 3 plus 1 all over 4 plus 1 over 1, while there's another fraction c over d that we did not know. Only this can make a over b between 34 over 109 and 47 over 151. So what is our c over d? Remember that it asks for the minimum of b. This means that we need only to find the minimum of d to get the answer. Why is it? Because if we simplify it to this form, we'll find that our a over b will be equal to 5d plus 4c all over 16d plus 13c. This means that d plays an important part in this whole fraction. Also remember that Farey sequences place fractions in an ascending form. This means when we get the minimum of d, we'll also find the minimum of c. So the answer for this question is to find the minimum of d, where c over d is between 3 over 7 and 1 over 6. How will we find d? Well, to answer this question, we'll use our old pal called computers. We'll list the Farey sequence of order 7. And then we find the number 3 over 7 and 1 over 6. Now we'll find the minimum of d between these two numbers, which is 3, and this means c over d is 1 over 3. Putting 1 over 3 into our continued fractions, and we can get our answer. A over b is equal to 19 over 61. This means the minimum of b is 61. So we solved our question. And that's all for today. Well, we aren't finished yet. We haven't talked about how we will find the fractions that we want. In the last example, we used the computer to calculate the Farey sequence, but we won't have a computer every time. You certainly will not want to find your fraction in such a Farey sequence of order 100. So please continue to watch the video and learn how we will solve these types of problems fully. First have to talk about one property. This is that a0, a1, a2 all the way to an-1 an will be equal to a0, a1, a2 all the way to an-1 an minus 1 and 1. We can prove this simply by expanding these two fractions. We can see that minus 1 will cancel out with 1 over 1, which means that these two are the same. Our goal is to find how we can use continued fractions to find fractions, and in what way will we find the minimum of the denominator in the fraction. So we'll look at a lot of different kinds of continued fractions in different forms and in different conditions. But let's first begin on Farey fractions. So let's explore Farey neighbors. So we've listed out a few Farey neighbors. Remind you that in this lecture, when we put a fraction on the upper row, this means that this fraction is lesser than the fraction below it. In this case, 7 over 8 is less than 4 over 7. So after we listed out the continued fractions form of these 8 Farey fractions, we can find that there are some interesting properties of Farey neighbors. We can first notice that these two will equal to 1 when they subtract each other. We can also notice that these two Farey neighbors also had this kind of similar property. Let's look at the two Farey neighbors below. We can find that all the way till a4, they are the same. But one ends till a4, but another fraction has another new number in the place a5. And on the right hand, we can find this similar pattern, where one ends with 4 and the other only has another 1 item in this continued fraction. So let's get to our first corollary of today, our corollary 1. If we express these two fractions a and b in these two forms, and let us let b is bigger than a. So how will we identify Farey neighbors? Well, firstly, if n equals k, that means a and b has the same number of items in their CF. If the absolute value of an minus bk equals to 0, then a and b are Farey neighbors. There are also other two conditions that will make a and b Farey neighbors. One is that if n minus k equals to 1, then if ai equals to bi, where I is bigger than 1 and less than k, then a and b are Farey neighbors. The same is true when k minus n equals to 1. but the range for I will be less than n. So these are the three forms that the Farey neighbors will express in continued fractions. We've already talked about how we will find the minimum between two Farey neighbors in the last lecture. We'll just simply add the two denominators together. So after talking about how Farey neighbors will appear when expressed in continued fractions, let's look at our problem. So before we look at our problem, let's think about how we will find the minimum of the denominator. If we want to get the minimum of the denominator, we have to notice two things. The items in the continued fractions needs to be as less as possible. That means that n needs to be as small as possible. While the last number in the continued fractions also needs to be as small as possible. So n and an needs to be as small as possible. Only in this way can we get the minimum. So let's go back again on our numbers. We can see that the parts 0, 3, 4, 1 are the same. The parts that are different begins with 2 and 5. Remember that we said that n needs to be as small as possible. This means that we do not have to consider our a5, which in this case is 3 or either 1, because we need n to be as small as possible to get our minimum. And now this means that we need to find a number between 2 and 5. Notice that we said that an needs to be as small as possible. This means that we'll choose the smallest possibility for a4, which in this case is 3. If we take 3 into 0, 3, 4, 1, 3, we'll find that this is really our correct answer for this problem. So let us now look at another example. First, we'll identify the similar parts, 0, 2, and 3. Next, we will need to think about 2, 1, and 3, because we need n to be as small as possible. Then we'll find the smaller number between 1 and 4 to be our a3, which in this case is 2. What we'll get is that 0, 2, 3, 2 is our answer. And if you use a Farey sequence calculator to look at the answer, you'll find that 17/16 is really our correct answer. It seems like we already have a system for how we will identify the minimum of the denominator between two fractions. But let us observe something that is interesting. In the left-hand side case, a4 will be closer to the smaller fractions a4, while on the right-hand side, our a3 will go with the bigger fraction. If we generate more and more examples like this in different digits and with different numbers of items, you can find one thing, which is our corollary 2. Our corollary 2 states that as a increases, the odd items will decrease and the even items will increase. This means that a2x plus 1 will decrease and a2x will increase as a increases. This corollary is extremely important when we need to identify which fraction is smaller and which one is bigger. Now we can conclude what we have found into corollary 3. If we want to find the minimum of the denominator in the fraction c, where we know c is between a fraction b and a fraction a, we'll first express a and b into the form of continued fractions. If ai equals to bi, where 1 is lesser or equal to I lesser or equal to m minus 1, and the absolute value of bm minus am is greater or equal than 2, then when 2 divides m, c will be equal to 0, a1, a2, all the way to am plus 1. Otherwise, if 2 doesn't divide m, c will be 0, b1, b2, all the way to bm plus 1. Our corollary 3 only expressed what we discussed earlier into the form of mathematics. If you put some numbers into it, you will quickly see that this is the same as we discussed. Now, there's a new condition. Why does the absolute value of bm minus am needs to be greater than 2? Well, let's look at what will happen if this absolute value is equal to 1. Well, we'll first identify the parts where they begin to become different. Well, you can see that if we want n to be as small as possible, we need an to be either 6 or 5 on the left example and an to be 4 or 5 on the right example. Remember our corollary 2, and this is especially important because we are going to use this to prove which one we'll to choose. On the left-hand side case, we'll choose a3 equals to 6. The reason of this is that if we express 0, 1, 1, 5 using our property, we'll get 0, 1, 1, 4, 1. From the corollary, we can prove that 0, 1, 1, 4, 1 will be greater than 0, 1, 1, 5, 1, 10. This means that if our new fraction c is 0, 1, 1, 5, c will not be between a and b, which is not what our problems want, and this is why a3 needs to go with 6. Notice that in this case, it is an odd item we are discussing, and it goes with a smaller fraction. We'll now look at the right-hand side case. It is the same for our right-hand side. a4 needs to be 5 because of the same reason. If we express 0, 1, 2, 3, 4 into the form 0, 1, 2, 3, 3, 1, we can find that it is lesser than 0, 1, 2, 3, 4, 5 using our corollary 2. And this is why our number needs to go with 5. Notice that in this case, our an is an even item, and it goes with a larger fraction. And this is how we'll get our corollary 4. If ai equals to bi, where 1 is lesser or greater than I, lesser or greater than m minus 1, the absolute value of bm minus am equals to 1, and n and k is greater than m, we can see that when 2 divides m, c will be equal to 0, b1, b2, all the way to bm. Otherwise, if 2 doesn't divide m, c will be 0, a1, a2, all the way to am. Notice another interesting thing. We've had a new condition here, which states that n or k needs to be greater than m. Why is that? Let's explore what will happen if n equals to m or k equals to m. You can see that in these two examples, we can rewrite our fractions using our property. In this case, 0723 will be equal to 07221, while 01213 will be equal to 012121. We can still use corollary 3 to solve these kinds of problems, which means we are back with our old problem and we don't have to discuss this. Now let's look at the last condition that might happen, n equals to k equals to m. Well, you can clearly see that this will just be Farey neighbors. That means that we've already discussed this. This means that the corollary are now sufficient for us to find the fraction c between b and a with the smallest possible denominator. So let us do a quick review. The first thing we talked about is a simple property like this. Then we talked about how Farey neighbors will be expressed in corollary 1. Then we talked about an important property of continued fractions in corollary 2. Then we used our observation and had corollary 3 and corollary 4. this is the end for our today's video. Using these 4 corollaries and our property, we can find our answer for any kinds of fractions when we put these fractions into the form of continued fractions. This means that this problem is totally solved. Thank you for watching the whole lecture. As you can see, I provided a complete solution for these kinds of questions, asking for the minimum of the denominator. This complete solution will help you solve these kinds of problems no matter how big the numbers are. You can still use this solution to be quick about solving these problems. I hope you'll watch the video again and divulge in the beauty of this solution. Also, you can get familiar with how this solution works. Our next lecture will be about geometry. You can guess the theme of our next lecture down in the comment section. Remember to share this video with your friends and give it a thumbs up. And that's about it. I'm Raymond Lin, and this is Strategic Math.